Good morning to all of you. Today we'll discuss the Unified Power Flow Controller. This is one of the major and having very unique characteristics. That is why they also name Unified Power Flow Controller. The unique characteristics are it can control all the parameters of transmission line which influence the power flow. That is, power flow is influenced by voltage of the sending end or receiving end voltage, impedance, and the angle of the voltage at which power is flowing from or power is flowing through the line. So this contains two voltage source converters. Voltage source converter has the unique characteristic that they can operate irrespective of the line voltage. That is, it absorbs or it supply or it maintains the voltage independently. The parameters that the line has does not affect the supply or absorb of the power. That is the unique characteristics of voltage source converters. So there are two voltage source converters. One is connected in series with the line. This is the transmission line, and through the series transformer it is connected, and other is connected in parallel to the line across the line, that is through shunt transformer. And the DC link of both the voltage source converters are connected via switch. So with the switch open, UPFC can be working as independent statcom, or it can be worked as a independent SSSC, and with closed switch it can work as a UPFC. That is also the main advantage of UPFC. So we will just see the advantages. UPFC is devised for real-time control and dynamic compensation of AC transmission system. Also, it is capable of controlling all the parameters that affect the power flow. The parameters which affect the power flow are voltage, angle, and the impedance of transmission line, either simultaneously or selectively. That means you can either control voltage and angle simultaneously, or if you want to control only angle, you can control that. Or if you want to control all the three parameters, that also can be done simultaneously. This because when we have seen the earlier facts devices, we found that TCSC and SVC, they could only control X. Then voltage parameter is controlled by statcom. Angle parameter is also controlled by the series compensator. So, but UPFC has the characteristics that it will control all the three parameters simultaneously or independently also. So it has unique feature of injecting voltage at any phase angle. In case of impedance type facts, we can add or we can inject voltage at quadrature or in phase. But UPFC can inject the voltage at any phase angle from 0 to 360 degrees. It can independently control real power. This is very unique because we know that when you want to transfer real power, it must be accompanied by reactive power. That is, without reactive power, real power cannot be transmitted or real power cannot be controlled. But UPFC can independently control real power. This we will see in detail in next slides. UPFC can control power flow as the direction as we have decided. Suppose we want to control power through one of the lines, then suppose one of the line is getting overloaded, we want to reduce the power flow, we can reduce by changing the parameters of that UPFC can do. So with DC common link, it can be operated as SSSC or STATCOM independently. Also, it has the advantages that we can get voltage regulation continuously with variable in phase and anti phase voltage injection. Since UPFC consists SSSC or series connected voltage source converter, voltage can be regulated or voltage can be inserted in series with the transmission line in phase and in anti phase, whatever value of the load situation is there, and that way we can control the voltage of the line. Also, reactive power can be controlled by injecting voltage in quadrature with the line. That is equivalent to capacitive or inductive, because you know when you add voltage in quadrature with the line, it will support reactive control. Then phase angle regulation is also achieved, that is by injecting series voltage with the desired phase angle without changing magnitude of the line voltage. Only phase angle is regulated here. Then the main advantage is that you do not require separate source or some sink for real power exchange. See, real power can be exchanged or it can be supplied or it can be absorbed if you have a voltage source. But here, or a sink, but here you do not require, because one of the end buses either provides or absorbs real power as per transmission line parameters. See, this whatever we have discussed is shown in this phasor diagram. Again, I have shown the diagram for UPFC, that is having series transformer to which voltage source converter is connected. This will inject voltage in series with the line. This is the shunt converter which is connected to the line through the shunt transformer. This will control the voltage across the buses. Now, in previous slide, as we have said, voltage regulation can be achieved continuously with variable in phase and anti phase voltage injection. So here in transmission line voltage, you add the voltage or you change the phase so that it will be in anti phase, so that whatever desired voltage you want, that can be controlled. So here, this is the transmission line voltage. Current is always perpendicular. So add the voltage either in phase with the line or anti-phase, so that you can regulate the voltage through voltage of the transmission line and hence the power. Here we are keeping the magnitude of the transmission line voltage same and changing the phase angle. That will alter active power. And this diagram indicates all the variations that we can do simultaneously. That is, we can change the regulation, we can maintain the regulation, we can add active power or we can control active power with maintained phase angle. So UPFC has these all characteristics which we have earlier discussed, which could be obtained by independent facts devices. Now, how it works? There are two voltage source converters, as we have seen. They are connected back to back, operated from a common DC link. That also we have seen, by storage capacitor that converts AC to AC, and we can exchange the power also. Common DC link facilitates real power flow in either direction between the AC terminals of the two converters. That means the capacitors, when they are connected by the switch, real power can be transmitted within the two converters. So there can be, say, suppose AC power which is converted to DC by the converter can again be converted by inverter action and can be supplied to the line. So each converter can independently generate real absorb reactive power at its AC terminals. This common DC link facilitates real power flow in either direction between AC terminals of the two converters. Also, we can see that series connected converter can inject voltage in series with the line and of controllable magnitude and phase. Thus, when the phase changes with respect to transmission line voltage, it's it exchanges real power as well as reactive power. When the phase angle is 90 degrees, it can exchange only reactive power. But when it is different than 90, it will exchange real as well as reactive power. Series connected converter that converts. Now see how it works. The actually series connected converter converts demand or excess of real power of transmission line to DC bus as supply or absorb of the real power. See, when the series converter injects voltage in series with the transmission line, since current flow through the, because it is connected in series, so current will flow through this converter and it will have power. So depending on the so that parameters will be measured by the controller of series converter, and that will be those parameters will be split into direct axis and quadrature axis, and real part of the power will be reflected or will be converted from AC to DC and will be will be given to the capacitors. Have you followed this? Series connected converter, when it injects voltage in series with the line, it will not be necessary in quadrature. It may have some, it will have some phase angle with respect to the transmission line current. So those component will be decomposed, and the direct axis component, which is the real part of the power, will be conveyed or will be reflected on the DC line, on the DC capacitors. And this is the, if the capacitor gets charged, it indicates that there is excess power in that real power. I'm talking about real power in the transmission line. So series connected converter converts demand or excess of real power of transmission line to DC bus. As if supply, if demand is there, it will be as if there will be less charging of capacitor. If excess of real power is there in the transmission line, it will be as if charging of capacitor. So this DC capacitor, depending on its demand or excess, whatever is the requirement of real power of transmission line, will be getting charged or discharged. And reactive power flow through DC link, no reactive power flow through DC UPFC, because DC does not allow reactive power to flow, so it is zero. But DC link converts the demand of real power of the transmission line. Are you getting this point? When the voltage is, I'll repeat, when the voltage is inserted in transmission line, see, this is in series with the transmission line, so series converter will insert voltage in transmission line. Then since it carries also current because it is in series, the power, real power of the transmission line will be communicated to DC bus. From AC to DC there will be conversion, and accordingly DC bus will have its appropriate charging or discharging. Now shunt converter supply or absorb the real power demanded by series converter at the DC link to support the real power exchange due to injecting voltage by series converter. That means, suppose the DC link is charged, it is having higher voltage, the shunt connected converter will give such a pulse that the excess of the real power will be fed back, because capacitor it also maintains the balance of the capacitor voltage. So shunt connected converter supply or absorb the real power demand of the series converter at the DC link to support real power exchange due to injecting voltage by series converter. The demand at the DC link is converted to AC by the shunt converter and it's fed back to the line via shunt connected transformer. That means shunt connected transformer will generate such a voltage magnitude and angle that the excess of power or the demand of power by the series converter will be met by the shunt converter, and this is fed back, or either if it is excess it will be fed back, if it is less, if it is required, if it is requested by the transmission line, it will be drawn from the sending end voltage or where the shunt converter is connected. Thus there is a closed direct path for real power exchange by series converter, then DC link, then shunt converter, then back to link. So this is the thing which does not necessitate reactive power to flow as per the requirement of active power. Up till now we used to say that, we used to see that if without UPFC, if you want to control real power, it must be followed by the reactive power, or without reactive power you cannot control real power. But because of this closed path for the real power exchange by series converter, then DC shunt link and shunt converter and back to line, there is no necessity to allow more reactive power or to alter more reactive power. This is the main characteristics. This is one of, because if with the flow of reactive power there will be losses in the transmission line, drop occurring, and voltage profile will be reduced, and all such problems are eliminated here. So reactive power generated absorbed by the series connected converter locally, and it meets the transmission line demand and need not be transmitted. Thus active power is supplied without change of reactive power flow. That means shunt compensator or shunt connected voltage source converter generates voltage as per the demand of the series connected voltage source converter. How it meets the demand? That shunt connected converter produces or generates voltage magnitude and phase in such a way that the demand is met by the demand of the transmission line is met by this. How it generates? That is controlled, or that is controlled by the converter, which will give finally the pulses for firing the thyristors. Thus the working of UPFC can be understood with, which has immense advantages like controlling all the power flow parameters, and without transmitting reactive power, active power can be altered, and angle of voltage can be from 0 to 360. Magnitude of the voltage that it can provide is within its rating of the UPFC. There are two voltage source converters are required. Disadvantages are there are two voltage sources are required, and voltage source converters, especially for transmission voltage, have very high cost. So total cost is very high for the UPFC as compared to other FACTS devices. Naturally, since this cost includes all the installation cost, its variable energy production cost, its cost per kVAR is also very high. That is, cost of generation of kVAR is high. There is no competition in UPFC manufacturers. and hence procurement installation is an exclusive monopoly of the supplier. Like SVC, there are, since I have told you, there are more than 800 SVCs connected all over the world. SVCs manufacturers, there are ample means more than one SVC, like Siemens, ABB, they all manufacture fax devices. So there is enough competition between the um, supplier. But in case of UPFC, there are no manufacturers, so hence it is only the monopoly of the supplier. There are only two installations of UPFC around the world due to its high cost as compared to this. And these two are in the, one is in USA, that is Inas, and other is in Gangjin in South Korea. This was installed in 1998, and in South Korea it was installed in 2003. Rating are also not very high. Here it is 320 MVA and it is just 80 MVA. As compared to other installations like SVCR 750, in India one SVC is at Raipur and one TCSC is at Kanpur. There no SSSC is installed because all the advantages of SSSC can be met by the TCSC as it is connected in series. So this is the, I'll show you, then we will go to MATLAB. This is again the programmable voltage source. This is equivalent to transmission line. Load is connected. So now see here, this line is connected. These two constitute UPFC, out of which this is series converter and this is shunt converter. So series converter is connected via like this in series. Can you see this? This is the path. Here the converter is connected. This is connected in series. And this is rest of the network. Again transmission line, one more bus. This is the load. Then this is the shunt converter which is connected in parallel to the line. This is connected in shunt. Okay. And the capacitor of this and capacitor of the series are connected through switch. This is the switch. This we will see in MATLAB environment also. This is the controller. Output of controller as it gives pulses for firing the thyristors. Because all these fax devices are nothing but semiconductor devices or switches which makes the which makes the relation between voltage and current as if lagging on leading. So, and this can be fired by using the controllers. For this controller, inputs are the wherever the UPFC is connected, their voltages. So this is the series connected voltage source converter. So the two voltages of this, so it is two voltages. Then the currents flowing, one is through series current, since series, and other is current flowing through shunt converter. And since we want DC voltage, because the capacitor voltage which is after effectively going to be converted to real power exchange, so we want here the measurement of voltage across the shunt capacitors and voltage across the series capacitors. This is the load that is connected. This is again the load. This is the generator. Have you followed the working of UPFC? Have you followed the working of UPFC? I will just repeat again. UPFC injects voltage in series with the transmission line. Since it exchanges real as well as reactive power, real power that is exchanged by the series converter is reflected on the DC link either they get charged or they get discharged or their voltage is reduced. This is from AC to DC conversion occurs, and capacitor or DC link is getting the appropriate or corresponding voltages. And since the switch is closed, this capacitors or the shunt converter, as per this voltages, generate voltage and phase angle in such a way that the excess power or the required power is supplied by the shunt voltage source to the line. Thus, there is a closed path between line voltage, series voltage converter, DC shunt, DC link, and shunt converter, and back to line. So with this, there is no additional reactive power required for compensating the real power, which will reduce the losses and which will make the system efficiency higher as compared to other FACTS devices. Now, since when the switch is opened, they can be used either as shunt converter. When the switch is open, it can be used as shunt converter. When the switch is closed, it can be used as UPFC, and also independently it can be used as SSSC. This is the main advantage, that same UPFC you can use as either STATCOM or SSSC or UPFC depending upon the switch position. Now, since there are three different devices in the same UPFC, they're all controlling parameters. Like if it is a STATCOM, you can control reactive power, VAR control. Again, if it is you are using it as a voltage control. So these all facilities which the devices supply or which it facilitates are shown here. If it is SSSC, you can control the voltage injection. Again, for STATCOM and SSSC, with these two, that is voltage control and voltage injection control, and UPFC control, which is the main, which uses both the controllers for controlling the power flow. Now we will see this power flow parameter only, because we have already discussed about STATCOM and SSSC. So here we have kept in this power GUI UPFC power flow control. Then we should set the parameters as the desired, and which is also within the rating, which is rating of the UPFC. It should be within the rating of UPFC. So it is 8.7, and then it will rise to 10 PU, it is per unit, in 0.25 time step. That means at 0.25 time step, 8.7 to 10, it will be, reference will be changed. And for reactive power, it will be from minus 0.6 to 0.7 in a time step of 0.7. So with this, then we can see the scopes. Now, since we will be doing only UPFC, there are STATCOM parameters which are shown, SSSC parameters and UPFC parameters. We will be interested in now observing UPFC parameters. So when the simulation is run, we have only set the values for power flow control, which is active and reactive power. Again, here path is the same. That is, we have to go to the start of MATLAB. Then here it is start of MATLAB, not the start of our PC. Then here demos. Then in demos, sim power system. Here again demos, facts models. And now we want to see UPFC detail model. Here, this will be the model which will have the description also and the working given here. Then run this model. That will open the model. Again, we will check whatever we have, whether the controls we have selected, it is yes, UPFC power flow, and the parameters for real and reactive power in per unit values with a proper time step. Then here also you can check configuration parameter, solver, it should be fixed step, discrete. You can mention here the time step, or if it is mentioned in here pointed here, it will do. So anywhere, or you can even mention in the callback function. See the scopes. This is active power per unit. Here it is reference and measured. This magenta color will give reference. Since we have given the time step of 0.25 from some 8.5 to 10, so this reference has changed. To come to that, by by generating appropriate pulses and trigger firing delay to the by the controller to the SSSC and STATCOM, this much time is required. That is nearly equal to 2.1.5. That is the time required, or the response time for the UPFC. Also for reactive power, here it is reactive power measured and reference. So at 0.5, it has changed from negative 0.65 to positive 0.5. So this much time was taken by the UPFC. These are the real active power shown by the every line, and reactive power shown by the line. So this is the thing which the controller has done, which has generated, or whatever we have discussed, that active power from DC link was communicated to STATCOM, and it has generated such a voltage that it will produce the required power. So this was the characteristics. Have, have you followed? Do you have any query?